Okay, we're going to do one more example where I show you all the steps in the course of a limiting reactant problem. We're going to find out first what reactant is a limiting reactant, and notice once again that we have the amounts of both substances, both reactants given to begin with. So we have to find out which one is going to be running out first. Then we're going to determine the theoretical yield of CO2. And ultimately use that information to find the percent yield. Notice that we have been given the mass of CO2 and also some amount of water. So we actually have the actual yields of both of those substances. And notice that question 3 is asking for the percent yield of water. So we're going to go after that as well. Then we're going to assume that the percent yield of CO2 is the same one as that of NaCl. And we're going to use that to find the actual yield of NaCl. And at the end, we'll also determine the amount of excess reagent left over. So most likely not, this video is going to be only half of these parameters. And then we'll have another one where we'll cover the last two. But let's get right to it. We're trying to find out the limiting reagent. So what we need to do is start with the amounts given. And the amounts given are the 10 mLs of H2CO and the 20.4 grams of sodium perchlorate, or NaClO, NaClO 4. All right, now we're going to have to use the density. So this right here, the grams per ml, that's the density of H2CO. The same way that the 0.9998 grams per ml is the density of water. Okay, so we'll use that in due time. But first things first, we are going to try to get both of these reactants ultimately into moles, such that when we have the moles, we switch over to the moles of CO2. All right, so for H2CO, we start with volume, and with the density, we can actually find out the mass. Notice once again that the 0.815 goes with the first unit, the grams. mLs has a placeholder 1 as the number associated with it. And since we start with mLs for the volume, mLs have to be on the bottom of this fraction. The grams need to be on top, and that's where the 0.815 needs to go, since that's the first unit in density. All right, this will give us the mass of H2CO. We already have the mass of of sodium perchlorate, the 20.4 grams. So we now have masses for both of the reactants. So here we can just kind of do the two in tandem, and we're going to go all the way to CO2. That's our reference product for the time being. All right, so we're going to use the balanced equation to make this happen. We have 2 moles of H2CO for every 2 moles of CO2. And in the same manner, we have 1 mole of sodium perchlorate for every 2 moles of CO2. So we use that as our premise. And in order to make that happen, we first need to convert these to moles, right? So we divide the mass of H2CO by the molar mass of H2CO, multiply by 1 mole, divide the mass of sodium perchlorate by the molar mass of sodium perchlorate. Now that the masses cancel out and you do have moles for the two reactants, you do use the mole ratio that I was talking about a little earlier. 2 moles of H2CO on the bottom, 2 moles of CO2 on top, 1 mole of sodium perchlorate on the bottom, 2 moles of CO2 on top, based on the balancing coefficients of those three substances. In this example, we are dealing yet again with the grams of CO2, so it'll be good to switch over the moles, which are canceling out, right? Now we have moles of CO2. It'll be good to switch over those moles of CO2 into mass of CO2, right? So 43.99 grams of CO2. All right, so the moles of CO2 cancel out. We only have now mass. So let's carry over the calculation. We have 10 multiplied by 0.815. Press enter in the calculator. Divide by 30.03, press enter. Multiply by 2, press enter. Divide by 2, press enter. Multiply by 43.99, press enter, and get the result. Similarly, start with 20.4 divided by 122.44, press enter. Multiply by 2, press enter. Multiply by 43.99, press enter, and you should find out the following answers for each one of those calculations. All right, since we are comparing the same product in terms of the amounts, all we do is we go with the number that is less in magnitude. And in this case, that means that the amount of 11.9 grams of CO2 is the upper limit of CO2 that we expect to get. We don't expect to get any more than this. And if we do, that means that our CO2 is impure. But this is the upper limit. What this also means is that the reactant from which the calculation got started with is automatically the limiting reactant. So it would be incorrect to say that 11.9 grams of CO2 is a limiting reactant. That is not true. CO2 is not a reactant, it's a product. What is a reactant is H2CO, and since that's the reactant from which this entire calculation derives, H2CO is the limiting reactant. At the same time, due to the calculation, we get the theoretical yield, right? So this calculation right here is automatically the theoretical yield of CO2. So we got two things out of this calculation. We got the identity of the limiting reactant and we got the the theoretical yield of the CO2 product. All right, so now we can calculate the percent yield of CO2. We have 9.57 grams of CO2 as the actual amount collected, 11.9 grams as the theoretical amount expected to be collected. So dividing those two numbers together, 9.57 by 11.9, multiplying by 100, cancels out the units and gives us a percent yield of 80.4%. All right, so this is looking pretty good. Okay, let's do one more, and that will probably be the end of this video. We'll find out the theoretical and percent yields of water. Since we know the identity of the limiting reactant, we don't need to redo this from scratch. We can simply just start with the limiting reactant itself, H2CO. We don't need to consider sodium perchlorate anymore. So, start with the 10 mLs of H2CO, use the density to switch over to grams. mLs go on the bottom, grams go on top, which is why the 0.815 is on top. And the mLs are on the bottom because you had mLs here to begin with. This will ensure that they cancel out. Now the grams need to be converted to moles, dividing by dividing by the molar mass of H2CO and placing the moles on top. All right, now up until this point, this is no different than the calculations we did before for finding out the limiting reactant. But now we're going to switch over to water. This is how this will differ. And for H2CO, we have 2 moles to begin with. For water, we end up with 2 moles, so the ratio is literally 2 to 2 or 1 to 1. 2 moles of H2CO on the bottom to cancel out with the 1 mole of H2CO on top, which leaves us with the moles of water. Now here we have mLs. I'm going to play a little trick on that, but we're going to first convert the moles of water to the mass of water using the molar mass of 18.02 grams for every 1 mole of water. So the moles cancel out and then you end up with the mass. I'm going to get that mass right now because I was running out of space. So the mass of water is 4.89 grams of H2O. All right, now this amount is technically the theoretical amount of water. So I'm gonna close it right there. There you go. We have 4.89 grams of water. All right, now the actual amount of water was 4.7 mLs, but the 4.7 mLs can be switched over to grams to compare it directly to the theoretical yield we just got. So we have 4.7 mLs. We're going to divide that by mLs, multiply by grams. In front of grams, we have 0.9998 as the actual number. So that 0.9998 needs to stick with grams. This will convert the 4.7 mLs of water into ultimately 4.7 grams of water if you round it up at the very end. All right, so now that we have the 4.7 grams of water, this is the actual yield of water in mass. The value right here is the theoretical yield. So we can find the percent yield by dividing actual amount by theoretical amount multiplying by 100. That's to say that 4.7 gets divided by 4.89 and we multiply that by 100. to get 96.1%.